want to take a look at what your book calls example 4 in the text. I'm not sure why they don't call it theorem 4, because it really is a statement of a theorem. But if r of t, now that's going to be a differentiable vector function, if the magnitude of that function is constant, then the derivative is going to be orthogonal to the function for all values of t. Now what I want to do is talk a little bit about what that means geometrically, and then see if we can't prove that. Okay, so if the magnitude of r of t is constant, well, if it's constant at 0, this is incredibly boring. We're talking about the constant function r of t is always the 0 vector. That's incredibly boring, and the 0 vector is differentiable and orthogonal to its own derivative, because its derivative would be 0. Okay, not interesting. Okay, but if the magnitude of r of t is constant and non-zero, that gets a little bit more interesting. Now in 2 space, if the magnitude of my vector function is constant, what that means is that the graph of that vector function has to lie on a circle. Now it doesn't necessarily have to be the entire circle. It could be part of the circle. I could be tracing the circle and I could just go back and forth over part of it again and again. But the graph would be all or part of the circle. And this is saying that the derivative has to be orthogonal to r of t for all values of t. Well, there are 2 options there. Either the derivative is the 0 vector. Now that could happen if I'm doing something like retracing the curve. Anytime I change direction, my derivative would be 0 at that particular time. But at the times when the derivative is not 0, that's going to take on a geometric meaning. If that's my r of t, what's perpendicular to it looks something like this. This is actually stating something that we knew from geometry, that the line that's tangent to a circle at a point meets the radius of the circle at that point at a right angle. Okay, so that's essentially what this is saying in 2 space. This is true in 3 space as well. So what does that mean? Well, if the magnitude is constant and non-zero in 3 space, again, if the magnitude is 0, the theorem is still true, it's just incredibly boring. But if the magnitude is constant, that would mean that my curve lies on a sphere. Now be very careful, it doesn't mean that the curve is the sphere, because the sphere is a surface, it's 2-dimensional. The curve is going to be 1-dimensional. You might be able to see, I took a marker and I drew some stuff on this curve. But that's essentially what we're talking about. The sphere becomes the surface on which I'm drawing my curve. I'm still getting a 1-dimensional curve, but it just lies on this sphere. That would be what we have if the magnitude of r is constant. And this says that this property, that the derivative is still orthogonal to the position vector, is still true. Again, that means either the derivative is 0, which could occur if I'm sort of pausing and changing direction at some time. But if it's not 0, that means that the derivative of any curve that lies on this sphere is going to be orthogonal to the position vector that's pointing to that point on that curve. Kind of cool. Let's see if we can't prove it. Okay. So let's suppose that we've got r of t is a differentiable vector valued function, and the magnitude of r of t is constant. Okay. Well, that's going to mean that the magnitude of r of t squared is also constant. It would just be that same constant squared. Okay. But that would mean that the derivative of the magnitude squared would have to equal 0. Because anytime I've got a constant, when I take the derivative of a constant, I get 0. Okay. So that's sort of what we're supposing in this case. I'm doing just an informal explanation of this. I'm not writing this up as a formal proof because it wasn't actually stated as a theorem. It's given as an example for some strange reason. Okay, but I know that the magnitude of r of t squared is the same as r of t dotted with itself. Remember, we've got that property of the dot product that if you dot something with itself, you get its magnitude squared. Well, that's kind of cool, because this is then telling me that the derivative of r of t dotted with itself has to equal 0, because this is constant. But we just learned that there's a generalization of the product rule for the dot product. So this would be the derivative of the first factor dotted with the second factor. So r prime dotted with t, r prime dotted with r, plus the first factor, r of t, dotted with the derivative of the second factor. And that's still equal to 0. I'm not trying to prove this equation is true. We know that's true because we're taking the derivative of a constant. I'm just trying to explore what that means. Now notice these two terms are the same because they're both the dot product of r and r prime. Remember, the dot product is commutative, so this is 2 copies of r of t dotted with r prime of t would have to equal 0. This is just a number. I'm multiplying it by 2. Let's divide both sides by 2. Well, r of t dotted with r prime of t would have to equal 0. And that's the definition of orthogonality. Okay. So that covers both the case where this is the 0 vector and the case where that's not the 0 vector, so that the derivative is actually perpendicular to the position vector at that time. So this is kind of a cool result. We are going to see it again. And generally what happens when we get a little later on in the semester, I say, we had a theorem a while back, does anyone remember it? Now it's not going to be nearly as much fun this semester because I'm not going to see the looks on your faces when I say that. But usually somebody will remember that I said, we're going to use this theorem, I'm going to refer back to it, and by the time I say that, you're going to have forgotten what the theorem is. And they're like, no, I vowed that I would remember this. So, I won't be able to see your faces, but vow that you will remember this when I refer back to it later on and see if you're able to keep to that.